We will be discussing how to estimate parameters for three types of regression models, including linear, multiple, and polynomial. Let's start with a simple linear regression model that will follow the equation form as shown. We will have an independent variable, also known as a predictor or explanatory, and a dependent or response variable. You can plot your points in a scatter plot. If we have an errorless prediction, then we will obtain a true regression line, which is perfectly straight. Realistically, there will be some error obtained. The random error term measures this. If it is positive, then the point is above the line, and if negative, then it is below. So, how do we estimate the parameters with a linear regression model? What this fancy formula is saying is to find the vertical deviation of a point from the line by subtracting the height of the point from the line. This is the least squares method. You will then sum the squared vertical deviations. You will obtain point estimates that create the estimated regression line. This will allow you to minimize the deviation from the point and line to get the most accurate regression line. Multiple regression is an extension of simple linear regression when we have two or more independent variables. Here I took a random number generator for three different variables and plotted them to see how they differed, which is pretty drastic. If you wanted to see how effective therapy is, let's say, you could look at the type of therapy, the length of time you have for the therapy, and the gender of the therapist to see which will give you the best results. To estimate the parameters, we will take the partial derivatives of f with respect to each b and equate all partials to 0 to get the normal equations as shown. These will be linear. Relationships are not always perfectly linear. Sometimes they are polynomial. This is the relationship between x and y to a kth degree polynomial in x. I have plotted a graph to show how these data points fit more of a curved path than a linear one. To estimate the parameters, we need to find the minimizing values. Take the k+1 partial derivatives and equate them to 0. You will obtain normal equations as shown for the estimates, which are linear. Let's say we're testing the proficiency of an artificial heart. An average heart at rest pumps 5 liters of blood per minute. For an artificial heart, we want it to pump around 7.5 to 9.5 liters, depending on the size and gender of the individual. We set up an experiment with different size artificial hearts to see the relationship between the size and the rate. We graphed the information we obtained to see the relationship and found it to be linear. We also found that between 50 to 70 cc's was the best size for what we need. This helps to use a mathematical approach because it is much more efficient than to use trial and error. Now we will see which size needs to be manufactured when building the machine. We estimated parameters through linear and nonlinear methods. The goal is to minimize our parameters as much as possible to obtain the closest value to our true regression line.